Okay, so welcome. This is the revision video of the topic, which is a regression. Now, what is the objective of regression? What we are trying to achieve through regression? We are trying to predict something, which we are calling as y, which we are calling as dependent variable with the help of independent variable, and right now we are denoting it as x. So y could be anything on the planet, right? Currently, the y is stock return, and we are trying to predict the stock return with the help of, say, GDP growth, inflation, management. Management is good or bad, R&D expenditure. So we are trying to predict the stock return. That what is the GDP growth? Just tell me the percentage. I will put down in a formula. The formula is y is equal to 1.5, 0.2 into x1, 0.4 into x2, 0.5 into x3, 1.5 into x4. Now, you're trying to predict it, but definitely you are not the god. You don't have the crystal ball to see the future. So, you will not be able to predict exactly that what would be the stock return in the future, and therefore there is error in the prediction. So, this is error in the prediction, right? And these B1, B2, B3, B4, this is called as partial slope coefficient. And 1.5 is what? 1.5 is called as intercept. What is the interpretation of intercept? Interpretation of intercept is that if x1 is 0, x2 is 0, x3 is 0, x4 is 0, then what would be the minimum stock return? Right? Now, GDP growth could be negative. GDP growth could be negative. Right? Inflation can also be negative. Management can be bad. So even x1, x2, x3 value can be negative, right? So it will decrease the stock return or it could be positive, right? Now, what is the interpretation of B1? B1, B2, B3, B4 as in 0.2, 0.4, 0.5, 1.5. The interpretation is that if if we just talk about this B1 as in 0.2, the interpretation of 0.2 B1 is that if x1 increases by 1 unit, then y, the stock return, will increase by 0.2 unit. What is the interpretation of 0.4, which is B2? The slope coefficient. And exactly it is called as the partial slope coefficient. If x2 increases by 1 unit, y will change by 0.4 unit, so and so forth. Now the question is, how you got the equation of this line? You got y is equal to 1.5 into 0.2. How you got 1.5? How you got 0.2? How you got 0.4? 0.5? How you got this God equation? This equation is called the regression equation. How you got this equation? How you got this B1, B2, B3, B4 values? How you got the coefficient value? That is what we have to understand. Okay? The next. Now, we had this equation. This is the regression equation. But when you apply this regression concept to find out this line, you cannot use this line until unless you have certain assumption which is fulfilled in this regression world, in this regression equation. The assumption is this equation is only valid for linear relationship between y and x's. There should be linear relationship between the independent variable x and dependent variable y. It cannot be true for non-linear relationship. But linearity in what? Linearity in parameters. What is the meaning of parameters? Your coefficients are called as parameters. Your coefficients are called as parameters. These are called as x1, x2, x3s are called as variable or features. Variable or features. When you enter into the discussion of machine learning, they will be called as features. Okay. So y is equal to b naught plus b1, x1 is square, right? Now, is it valid? Yes, it is valid because you want the linearity in the parameters and the coefficient. So it is a valid equation. You can apply the regression logic to find out your b naught and b1. But if this is the equation y is equal to b naught plus b1 square into x1, this is not valid. This is not valid because there is no linearity in the parameter. There is a quadratic relationship between the y and x, and that is getting imposed with the parameter of b1 square. So it's not a valid equation. That's why there is a cross there. One and the most important line of the assumption, if you remember this line, you will remember all the assumption in the regression, is this line number 2. The error term is independently normally distributed with a mean of 0 and a constant variance. Error term should be independent. When I say the word independent, it means that error term is not related to anything on the planet. Error term is not related to anything in the planet means that the error term is not even related to itself, the previous value of the error term, or previous to previous value of the error term. And the error term, the error in the prediction is not related to this x4, this x3, this x2, this x1. It is completely random and it is normally distributed. Error term is normally distributed with a mean of what? Zero. The mean of error term is zero. So there is a lot of error term E1, E2, E3. When you take the mean of it, it will come to zero. And it has to have a constant variance. The error term, the standard deviation of the error term in the prediction would be constant. Okay. Now, the third is that there should not be any multicollinearity. What is the meaning of multicollinearity? The meaning of multicollinearity is these independent variables should not be related to each other. There should not be a very high correlation between x1 and x2 and x2 and x3 and x3 and x4. Apart from that, it should not be such that x1 is a linear combination of x2 and x3 or x4. Similarly, x4 is not a linear combination of x1 and x2. So there should not be any linear relationship between x1, x2, x3, and x4. There should not be a very strong correlation. Okay. With these assumptions, this assumption will get repeated again and again, because if these assumptions are not valid, that will lead to a lot of problem, like problem of heteroscedasticity, multicollinearity, whatnot. Okay. With that, we'll move into the discussion of that actually how will you get this B1, B2, B3, B4 assumption is over. We'll rediscuss the assumption later. So how to get the equation, as in how to find your B0 and B1 or B2, B3, B4? Let's first understand easily for a simple linear regression, as in you have only one variable, that is simple linear regression, only one independent variable, and with the help of that one independent variable, you are trying to predict your Y. Okay. So basically, what you're saying, this is your dependent variable which you are trying to predict, and you're trying to predict with the help of X. Actually, you're trying to find out the equation of this line, right? And the way you're trying to find out is you're trying to find the best fit line. What is the definition of best fit line? Let's understand. These are actual data point. So for example, X is GDP growth. Currently, say that whenever the GDP growth was 5%, the stock return was say 10%. So there would be a data point, say this is that data point. When GDP growth was 1%, then stock return was 2%. This is another data point. So these are the different data point, old data point, which we already know. We plotted those data points. So therefore I have written old data or old data points. Okay. And you're trying to fit the best fit line. You're trying to plot the best fit line. What is the best fit line? The best fit line should be such that what you have, what are these actual y, and what you're trying to predict with the help of this best fit line. This is your prediction through the best fit line, and this is your actual y. The difference between them is called as error. That is error, and that error has to be what? Minimized. So there would be multiple error. For example, you're trying to predict something here with a certain value for the certain value of x. You're trying to predict something for the certain value of x. So there would be certain error, that is actual values, minus the predicted value. So that is called as error. If you try to minimize the error, that is what is the best fit line. So what is my objective? Minimize the error. How would I get the error? That is the actual y values and the predicted y values. From where you predicted the value? With the help of this equation. Okay. And that is what? The remaining is the error. You're trying to minimize the error. Now, when you try to minimize the error, what will happen? See, in this scenario, if you can see that right now, this error is positive. Here, the error is negative. This is y actual minus y predicted. If you do, it will come positive. And when you do y actual minus y predicted, it will come negative. So positive, negative will cancel out each other. So the summation of error term will come to zero for a lot of different line. Even for this line, the summation of error term will come to zero. I can prove it. But this is a revision video, so we will not prove it right now. So the summation of error term will come zero for a lot of good lines. So that is not the objective. We have to find the best of all. So what we can do, instead of doing summation of error term, why not do summation of error term square? Minimize it. Minimize this, because summation of even square is all the values will come positive and you're trying to find out the line for which it would be minimum. Okay, so you try to minimize it. Now this is also one another benefit even from being positive, as in I square is positive, that higher the error, more you penalize the line. So if for a given data point the error is say 5 and for another data point the error is 2, you will penalize this point. So whenever the distance from the actual and the predicted, the distance between the actual and the predicted is high, you're penalizing that line and you're trying to minimize. So you will get only one line which would be the best line, where you get the minimum of all, the minimum of all. And how you minimize? So summation of error square. Summation of error square is what? Actual minus predicted square, which is y minus y hat. So what is predicted? Predicted is always called as y hat, which is your equation b naught plus b1 x1. This is called as predicted. So what is y? Y is y hat plus error. Y hat plus error. So y is equal to b naught plus b1 x1 plus error. Okay, you should remember that when you need to write y hat and when you need to write y. Okay, y is always with the error. Y hat is not without the error. It is the predicted value. Okay, when you do the subtraction, you get what? Get the error square. Then you try to minimize it. In any minimization process, in any optimization process, you minimize with the help of what? Differentiation. So you're doing differentiation, and when you differentiate it with b1, then you will get equated to 0. That is the basic optimization maxima minima. You don't have to remember it. If you solve this differentiation, if we solve this optimization problem, b1 will come as covariance of xy upon variance of x, or r sigma y upon sigma x. This is nothing. If you remember the portfolio discussion of CFA level 1 or FRM level 1, then beta formula is this. Beta is covariance of x comma y, covariance of market with the stock divided by this variance of the market, or r sigma of the stock upon sigma of the market. So that is the beta formula. That is the same beta that you derived for this particular equation. Okay. Now, you got the b1 in this equation. What was my objective? My objective was to find this equation b0 and b1. I got my b1, that is r sigma y upon sigma x, or covariance of x comma y upon variance of x. Then I will put it in this and will find the value, but I don't know, because this y is actual y and there is an error term. I don't know that error term. So what we'll do? The trick is, the equation is y is equal to b0 plus b1 x1 plus error term. Take the mean both sides. So this is y mean. The constant value b0 is a single constant value. The mean of the constant is going to be constant. So b0, b1 x1. Now b1 we already know, and this is constant. That is r sigma y upon sigma x. Then x1 mean is what? X mean. Now you know the b1, you know x mean, because you already know what is the old data. You take the x mean, you take the y mean, and you can find out b0. So b0 is y mean minus b1 into x mean, because you already know the value of b1 from r sigma y upon sigma x, or covariance of x comma y. One important point. When you written this line, y mean is equal to b0 plus b1 into x mean, when you wrote this line, you are also saying that if this is x mean, then this point has to be what? Y mean. Okay, so b0 is equal to y mean is equal to b1 minus b1 x mean. Okay, now I just want to tell you one thing, that this is not that it is only valid for simple linear regression of one variable, b2 x2 b3 x3. The whole method of differentiation, if you apply the whole method of differentiation, at the end your equation will form will be get resolved in the differentiation and the optimization problem, that your bi, all the coefficient b1 b2 b3 b4 value would be covariance x of xi with y. Now there is not only one x, there are multiple x, so there would be a covariance matrix of x and y, and the covariance of xi, all the independent variable x1 x2 x3 x4, the covariance matrix of all the independent variable. And if you do the division of that, you will get b1 b2 b3 b4. So every time this formula will work, whether it is simple linear regression or multiple linear regression. However, this is not in the curriculum of FRM or CFA, all the levels. But if this would be the question, you may encounter this in the in future when you do the proper optimization or you try to find out the B0, B1, B2 in your optimization equations. Next, now we got our model, that is this model, right? Whatever the value of B0, maybe 1.5, B1, 0.2, whatever the value, we got our equation. Now we need to analyze our model. This is our model. This is our regression model. How would you analyze? You first analyze with something called as R square. Then you perform test, T test, F test. Why you perform T test? You perform T test whether your coefficients are good or not. It is only the test of coefficient. However, when you perform F test, then you're understanding or you're trying to understand that how your overall model is performing, not just one coefficient, how the overall model is performing. Okay, so first we'll understand what is R square, which is also called as the explanatory power of the model. Then we'll understand the T test, and then we'll understand the F test. So without delay, let's enter into the discussion of R square. First of all, nobody knows or nobody speak out the real definition of R square in the interview. So it's important that you understand what is R square. R square is not that you explain this section of Y. No. Exact definition of R square is how much variability in the Y can be explained by your model. Assume the variability of Y is this. This is the variability of Y. And you're able to explain this green section, which is 80%. How much variability you can explain? Can you predict the Y? No, this is not the definition. You are able to predict the Y value exactly by 80%. That is not the definition of R square. R square definition is how much variability in the Y you can explain with the help of your model. So when I say R square is 80%, it means if the variability of Y is this, I can explain 80% of that section. And if the variability of Y, say R square comes as 70%, I can only explain 70% of that section through my model. That is the definition of R square. It is always in the terms of variability. You say, I can predict the Y 80%. No, that's incorrect. Okay. Now let's understand that how can you develop the formula. We know the variability of Y is what? Y minus Y mean whole square upon something n minus 1 or whatever. That is the variability of Y, right? So first of all, let's plot our Y hat and Y mean. So this is my actual Y. Why I need Y mean? I need Y mean because Y minus Y mean is the variability of Y. Y minus Y mean whole square is the variability of Y. This is the total variability of Y. Now, for this given X, I am able to predict this Y hat. What is Y hat variability? This is the variability of Y hat. Y hat minus Y mean. Because the mean of Y hat is going to be Y mean any day. Right. So Y hat. Why the mean of Y hat is going to be the mean of Y? Because you write Y is equal to Y hat plus error term. When you take the mean both sides, the error term mean will become 0. So Y hat mean is going to be Y hat mean. Okay. So Y hat mean is also Y mean. So Y hat minus Y mean whole square will give you the predicted variability. Now what I'm saying, this is the section you are able to, this variability you are able to explain with your model. And this is a section which you are not able to explain with your model. Right. What is this section? This section is summation of Y hat minus Y mean whole square. What is this section? This section is Y minus Y hat summation whole square. What is the total section? The total sum of square, that is Y minus Y mean whole square. So in this total, if you are able to explain this section, then if I say what is R square, what you will do? You will say explained upon the total. You will say explain upon the total sum of square. So let's understand. So let's understand with the help of the terminology. What is the total variability in the Y? Total variability in the Y is Y minus Y mean whole square. What is the explained variability? This section is my explained variability, which is Y hat minus Y mean whole square. What is error in the prediction? This section is the error in the prediction, that is y minus y hat whole square. We call it as RSS, regression sum of square, SSC, sum of squared error, SST, sum of squared total. Now this terminology is only valid for CFA curriculum, RSS, SSC, SST. For FRM curriculum, it is the regression sum of square is called as explained sum of square, and sum of squared error is called as residual sum of square, and SST is called as total sum of square. Okay, however, coming back to R square. What is R square? How much you have explained in the total variability. What is your explained section? This is your explained section. What I'm calling it as? I'm calling it as RSS. The section that I have explained, I'm calling it as RSS, which is nothing y hat minus y mean. Y hat minus y mean whole square. What is the total? The total variability in the y. This is the total variability in the y, which I'm calling as SST, sum of squared total. And this is summation of y minus y mean whole square. Now this RSS can also be written as what? Total sum of square or sum of square total minus sum of squared error. Because the sum of squared total, this total variability is what? Regression sum of square plus the sum of squared error. This formula. Okay, so I can also write in this format. So R square is always RSS upon SST. Now in FRM curriculum it will change. There the formula would be ESS upon TSS, because there the explained section is called as explained sum of square, not regression sum of square. Okay, so this is the difference. So we discussed R square. I'm repeating, the explained is called as, or the regression section is called as, what is the explained section? I'm repeating again, this is the explained section, this is the explained section. This is called as in CFA RSS, in FRM ESS. The unexplained or the residual part is called as SSC. In CFA, that is sum of squared error, and in FRM it is called as residual sum of squared. In the total, in a CFA, the total variance is called as sum of squared total, and in FRM it is called as the total sum of square. With that, we can also create an ANOVA table. Now, I'm just talking about in the terms of CFA curriculum. You can, if you are just studying for FRM, just remember that for FRM, the notations are slightly different. However, the intuition and the logic is same, both in CFA and FRM curriculum. So regression, RSS, error, SSC, total, SST. Now, if you remember, whenever we used to find out the standard deviation of anything, the sample standard deviation is divided by n minus 1. So the total, the standard deviation of y should be divided by n minus 1. And what is n minus 1? The degree of freedom. The degree of freedom. Now, RSS degree of freedom, let's understand the regression degree of freedom is what? Your regression equation is y hat is equal to b1 x1 plus b2 x2, right? Plus b3 x3. How many independent variables we have? We have only 3 independent variables. So your regression degree of freedom is the number of variables that you have. The regression sum of square, when you do this y hat minus y mean, this is your regression sum of square. You don't divide by n minus 1, because the degree of freedom that you have is only because of the independent variable that you have, that is k. Okay, now we learned that, just a second, we learned that the total sum of square is equal to the regression sum of square plus sum of squared error. Now the total sum of square degree of freedom is equal to the degree of freedom of RSS plus degree of freedom of SSC. Now the total sum of square degree of freedom I have already mentioned, it is what? Just a second, I don't know what has happened. Just now the degree of freedom of total sum of square is equal to degree of freedom of RSS plus degree of freedom of SSC, because total sum of square is equal to RSS plus SSC. Now the degree of freedom of total sum of square I am writing as what? N minus 1. See, n minus 1, this is the basic standard deviation degree of freedom. So I am writing it as n minus 1. Degree of freedom of RSS, the regression degree of freedom, is only dependent upon the number of variables that you have. So right now I have 3. So I'm writing it as k. K is the denotation for the number of independent variable in your model, plus degree of freedom of SSC, sum of squared error. So what should be the degree of freedom of sum of squared error? It should be equal to n minus k minus 1. So that is what is written. Now, if you divide the sum of squared error with n minus k minus 1, it is called as mean squared error. And you need to divide because then you will get variance or standard deviation. Because even in the total sum of square, you're dividing with the degree of freedom. So even for the regression, sum of square, you divide with the degree of freedom. And for MSC, you divide with the degree of freedom of the sum of squared error, which is n minus k minus 1. And how we got the degree of freedom? I proved it. Now, this is ANOVA, which you will see in your curriculum. Now, moving to the last discussion of R square. But just for satisfaction, let's repeat what is MSR, MSC, and standard deviation. So let's see. If I ask you to find out the standard deviation of y, what you will do? You will do summation of y minus y bar whole square upon something. What is that something? That something is degree of freedom. Yes, no, right? That is the formula of standard deviation. Yes. Okay. Now, if I have to find out the standard deviation of error, right now the sum of squared error is what? It is just summation of y minus y hat up whole square. This is sum of squared error. This is not the standard deviation of the error. To find the standard deviation of error, I need to divide by the degree of freedom. Yes, that degree of freedom is n minus k minus 1. And that is called as MSC, not directly standard deviation of error. Similarly, MSR is what? Y hat minus y bar whole square. This is the standard deviation of y hat. But you cannot divide the standard deviation of y hat by n minus 1. You should divide by the degree of freedom. And the degree of freedom of y hat is k. Why it is only k? Because your y hat is only dependent upon 3 variables. Okay, understood? Now, where they are used, we'll talk about it in a minute. Now, let's talk the last discussion in R square. Now, R square, adjusted R square. Why not only R square? Why adjusted R square? So assume you have a model y is equal to b0 plus b1 x1 plus b2 x2 plus error term. Now the R square is 70%. Now whenever you try to add another variable, so you try to add another variable from what? Actually the section that you haven't explained. So you will throw some error. So if you throw some error as a variable, so basically it will become b3 x3. So you're adding one variable. So your error will decrease. Now, if your error will decrease, then what will happen to the explained section? Will it increase or decrease? It will increase. Because in the total sum of square, you are saying the error section is decreasing. So what section is increasing? The explained section is increasing. So R square will every time increase if you increase the number of variables. So you see the R square is now increased by 5%. Now it is 75%. So every time you keep on adding a new variable, what it will do? It will increase the R square. Now you can add 100 different variables. Now it is good to say, okay, for prediction of the stock return, let's add 100 different variables. So, but it will increase the computational requirement from your computer or whatever you are using, right? It's not a good practice to have a lot of variable, because first of all it will be very complex for you, and it will be very complex to code, and it will be very complex for even the algorithm to run. So you always want the model to be parsimonious. What is the definition of parsimonious? That your model should have as much as less variable possible, such that your R square is optimized. So every time you do not want to keep on increasing your R square number. So for that, you fall back to something called as adjusted R square. Now adjusted R square has certain formula, we'll talk about it. So you calculate adjusted R square. So you calculate adjusted R square of the first model. Now this model give adjusted R square of 65%. Now another model, the same model, when you're adding the B3 X3, it is giving the adjusted R square of 60%. Now you understand that when you are adding the variable, the new variable x3 to predict your y, it is not beneficial to add to the model because your adjusted R square is actually falling. So you always compare adjusted R square whenever you try to add more number of variable instead of R square. Now, what is the definition of adjusted or the formula of adjusted R square? This is the formula of adjusted R square, and it is very well formalized. So, if I put down k is equal to 0, what is k? K is the number of independent variable that we have. So, you see, this formula will throw R square itself. So actually in this formula, there is a fight between R square and K. So every time you jump into a higher dimension, when I say higher dimension, basically you're adding more variable. When you're jumping to a higher dimension or adding more variable, your R square will increase. But this formula, the K is in denominator and it is after the subtraction. So it will try to decrease it. So in adjusted R square is increasing, but K is trying to decrease it. So there is a fight and K is the number of independent variable. Let's take a very basic example to see that adjusted R square, the K will try to decrease the adjusted R square. See, your R square is 60%. Now adjusted R square formula is 1 minus n minus 1. What is n? N is the number of observation. What is the number of observation? So the number of observation of the data. So for example, you have collected the data of stock return for say 5 days. So that is the number of observation. So number of observation, now your model has only one independent variable. So k is 1, so it would be n minus 2. So when you solve it, so it will come 4, it will come 3. So 1 minus 4, so when you just as in open this bracket, so 1 minus 4 upon 3 plus 4 upon 3 into r square. So 4 upon 3 into r square minus 1 upon 3. So you will see that r square is 60%. So 60% into 1.33 minus 0.33, it is coming to 0.46. See, even the r square is 60%, adjusted R square is throwing what, 46%. See, what I'm trying to highlight that the K is trying to fight against R square. It will pull the R square to a lower value. This is how the formula is designed, and therefore it is always advisable to compare adjusted R square when you are moving to a higher dimension or adding more variable to your model. Now, t-test. What is t-test? T-test is only testing your coefficient. It is not the model test, remember. So you're testing B1, B2, B3. Why are you testing B1, B2, B3? What if there is no relationship between Y and X1? But your model is saying B1 is 0.5. What if it is 0 only? What if B2 is 0? What if B3 is 0? What if B3 is 0? What if there is no relationship between Y and say X1 or X2? So what I'm trying to highlight, for this training data, for every model you have to give the training data. You have to provide some data to the model, so they will give you B1, B2, B3, some observation has to be given. For this training data, B1 is not equal to 0. What if for the next, the B1 is actually equal to 0? For this training data, B1 is not equal to 0. For what if for another training data, it will be equal to 0? So how will you test that your B1 is actually significant? Your B1 is actually significant. Your coefficient is actually significant. And for that, you do t-test. Why t-test? Because it has been assumed that B1, B2, B3, the coefficients are t-distributed. With a mean of 0 and the standard deviation of B1, whatever the standard deviation of B1 would be, right? The standard deviation of B1 and the mean is 0. Now, whether you take mean as 0 or not, because sometimes the mean changes based on what is your hypothesis, but the standard deviation of B1 would be there. What I'm saying that B1, B2, B3 are t-distributed. That is the assumption. How it is t-distributed? Let's understand. Right now, for the training data, this is giving me B1 of 0.2. For the next training data, it will give me the B1 of 0.3. For the next, it will give 0.3 again. Then it will give 0.4. Then when you plot all the B1s for the different training data, it will come t-distributed. That's what I'm trying to say. Okay, even if you don't understand this, just remember that it is t-distributed. The coefficients are t-distributed. Now, y is equal to 1.5 plus 0.75 into x1 plus error. Now, I want to test whether this 0.75 is actually significantly away from 0 or not. So what is my t-statistics? Why I'm talking about t-statistics? Because in any test, any distribution test, you need what? Whether it is normally distributed, t-distributed, chi-square test or f-test, you need a boundary and you need a ball. Now you will throw the ball and check whether the ball is falling in this region or this region. If it is falling in the left of the boundary or the right of the boundary. What is your boundary? Boundary is your critical value, which will come from generally the table. where you have to provide the significance level. From where you get the ball, you will get the ball with the help of statistics. So here the t statistics is whatever your b1 value minus 0 upon standard deviation of b1. It is very similar to x minus mu upon sigma, or you can say it is equal to be tested, which is 0.75 minus null hypothesis upon standard deviation. But what is my null hypothesis? What is actually my null hypothesis? My null hypothesis is this. My null hypothesis is B1 is equal to 0. What is my alternate hypothesis? My alternate hypothesis B1 is not equal to 0. What I want? Do I want B1 equal to 0 or B1 not equal to 0? Pause and think about it. If you see, you have worked pretty hard to develop your model. You want your B1 not equal to 0. Okay, so 0.75. Now the standard deviation of B1 is given 0.15. Okay, the degree of freedom is always n minus k minus 1 in the case of t-test. It is always n minus k minus 1 for t-test, the degree of freedom that you will take. Okay, and the t statistics is what? 0.75 minus 0 upon standard deviation of, you got it, 5. Now this is your t statistics, which is a ball, but you need a boundary, which is your critical value, which will come from what? Degree of freedom. What is the degree of freedom? N minus k minus 1. This is the degree of freedom that you will use in the t-test for the coefficient testing. That is n minus k minus 1. What is n? N is the number of observation. What is k? The number of independent variable. What is 1? It's 1. Okay. Now, so you got the degree of freedom as 18, and now you need to go for what? T distribution. Now, assume the significance level is given as 5%. So see, you have to create two boundaries. Why two boundaries? Because t-test is a two-tailed test. Because the b1 could be also negative, right? B1 could be a value of minus 0.75. So it is a two-tailed test, not a one-tailed test. Now significance level is 5%. So this is your significance level, 5% for two-tailed test. What is the degree of freedom? Say the degree of freedom, there are three variables. Assume there is only one variable. So the degree of freedom is n minus k minus 1. So it is 18. So let's check for 18. For 18, you're getting a value of 2.101. So your boundary is 2.101 positive and your boundary is negative 2.101. Okay, this is CFA level 1 and FRM level 1 stuff. The basic of hypothesis testing. Okay. Now, if B1 is equal to 0, you are sad. If B1 not equal to 0, you are happy. Your model is correct. Now, what is your t statistics? It is 5. Is it right to the boundary or left to the boundary? This boundary. It is a positive value, so I will just check this boundary. So it is right to the boundary or left to the boundary? Right to the boundary. This is your 5. What I'll say, this 5 is very far from 0 because it is beyond the boundary. If the 5 is here, I would say no, the 5 is not very far from 0. Right now, the 5 is beyond the boundary. So I will say the 5 is very far from 0, and therefore I will reject my null hypothesis. I won't say that I will accept my alternative hypothesis. I will say I'll reject my null hypothesis and I'm happy that B1 is not equal to 0. Okay. Now there is another way through which they will give the values, where you don't have to find t statistics, where you don't have to find the critical value. They will just speak that the p value is 1.5%, significance level of 5%, tell whether you accept null hypothesis or reject null hypothesis. Same example, this is your null hypothesis, b1 is equal to 0, b1 not equal to 0. They will not give you n value, or they will not give you a standard deviation of b1. They will not give you the t statistics. Any value they won't give. What they will give only, the p value is 1.5% and significance level is 5%. First of all, let's interpret what is p value. P value is the area under the curve from the tail for t statistics. You just calculated your t statistics, which came to what? 5. You are saying that if you put 5 here and if you try to cover the area from the tail, it will cover only 1.5%. Okay. Now your significance level was 5%. It means that you have to cover how much? 2.5%, 2.5% in each tail. So definitely 1.5% is less than what? 2.5%. And I will say that 0 is far from the 5 or the p value of 1.5%. and therefore I will reject null hypothesis. But if the p-value came to 3, then what it means, cover the area from the tail for t statistics. It is saying that if you calculate your t statistics, you will cover the area till 3%. And this is only 2.5%. Your boundary is standing only at 2.5%. Your boundary is only standing at 2.5%. Right? This is 2.5%. This section is 2.5%. And the p-value will cover till this area. So your t statistics is very near to 0. So what I'll say, that I fail to reject null hypothesis and my b1 is equal to 0. So sometime in the question they will only talk about p-value on the significance level in the question, and then you have to tell whether you reject the null hypothesis or fail to reject null hypothesis. Understood? Now, okay, so there is a one important stuff that I missed, that how you got the standard error of b1. Actually, there is a very exhaustive formula for the standard error of b1 or standard error of b2, but it is dependent directly on the error in the prediction. Basically, your model is what? Your model is y is equal to b0 plus b1 x1 plus b2 x2 plus error term. The standard deviation of error term, if the standard deviation of error term is higher, then what I'm saying, the standard error of b1 is also higher. So basically, standard error of b1 or standard error of b2, standard error of b3 has standard error or sum of squared error in the formula of b1, b2, b3. So higher the variance of error term, higher the variance of error term, higher the variance of error term, higher would the standard deviation of b1, b2, b3. Higher the variance of error term, higher the standard deviation of the coefficient. Higher the standard deviation of error term, higher the standard deviation of coefficient, then your t stats value would be low. Why this is important, you will understand in the assumptions. Okay, so you just have to remember that the standard deviation of coefficient is directly proportional to the standard deviation of error term. That's it. Higher the standard deviation of error term, higher the standard deviation of coefficient. Now, f-test. Now, f-test is the overall model test. It is not testing an individual coefficient. So you develop your model y is equal to b0 plus b1 x1 plus b2 x2 plus b3 x3. With a lot of hard work, you develop this model. Now you have to test the overall model. Okay. So the null is b1, b2, b3 all are 0, or any one of them is not 0. That is your alternate. If you can protect any one of them, your model is protected. Okay, the coefficient is incorrect, but your model is protected. So any one of them is not equal to 0, or your H null is what? B1, B2, B3 all are 0. That is your H null H alternate. If even B1 came not equal to 0, that's fine. That's fine. You protected your model. Again, there would be some distributions. There would be a boundary, which will be called as critical, and there would be F statistics, which would be the ball that you will throw. And this is 0. This point is 0 because this is right skewed distribution. How you get critical value? Every time the critical value, for critical value, you need what? Table. In the table, you have to throw what? Significance level, and the significance level should be given in the examination because it will come directly from the researcher. For F critical, you need what? The numerator degree of freedom and denominator degree of freedom. Why you need denominator and numerator degree of freedom? If you remember the F table for different significance level would be different table, and it will say the degree of freedom in denominator and degree of freedom in numerator. So the top row is the degree of freedom of numerator, leftmost column is the degree of freedom of denominator. So you need the degree of freedom of numerator and denominator to read the F table to find out your critical values. The critical values always come from table, whether it is T, whether it is normal, whether it is F. Okay. Now what is the formula of F statistics? It is saying mean of explained. Have you done mean of explained somewhere? Have you done mean of explained somewhere? Yes, no? So we did it. We did it in MSR, MSc, and the standard deviation of y. So you are saying mean of explained divided by mean of error. Your F statistic is saying explained upon error. In simple term, you want it to be higher or lower, or higher the better. It is saying explained upon error. You want it to be higher or lower? It is saying explain. You want it to be higher because you want to explain more and you want the error to be low. So explained, the numerator will increase and the denominator will decrease. Yes, no? Okay. Now mean of explained upon mean of error. What is explained? Regression sum of square. What is the degree of freedom? K. So you divide with the degree of freedom of RSS. RSS degree of freedom is K. Why RSS degree of freedom is K? Because RSS stands for regression. And the regression Y hat is only dependent upon 3 variable or 4 variable, which is your K. Sum of squared error. We just proved that the sum of squared error degree of freedom is n minus k minus 1. So you divide with the degree of freedom of n minus k minus 1. Have you got degree of freedom of numerator? Yes, no. Have you got the degree of freedom of denominator? Yes, no. Yes, you got the degree of freedom of denominator and numerator. You will look into the value of degree of freedom of numerator denominator with the significance level, and you got your critical value, you got your F statistics. Now understand, you are saying F statistics higher the better or lower the better? You're saying higher the better. So if F statistics is falling in this region, a higher value, you will reject your null hypothesis because the explained section is very much higher than the error. And if it falls in this region, then you are saying that explained is 0, very near to 0. Your model is pathetic. Now moving into one example, say the significance level is 5%, n is 15, and your model is this. Find F critical. How you will find F critical? For F critical, you just need significance level. So which table you will read? This one, because this is for the significance level of 5%. N is given 15. How you will find, tell me how will find the F critical. See, N is 15. Now the numerator degree of freedom is going to be what? K, which is what? 3. The denominator is n minus k minus 1, which is what? 15 minus 3 minus 1, which is what? 11. So you have to look for 11 and you have to look for 3. This is your critical value, 3.59. Then you calculate your F statistics and compare. If this is 3.59 and if your F statistics is 5, you will reject your null hypothesis. Your model is behaving pretty decently. Okay, now moving to the final discussion of F test. So your null hypothesis was what? B1, B2, B3, everything is 0. The model is pathetic. H alternate, any one of them is not equal to 0. At least one of them is not equal to 0. If F statistics fall in this region, you are sad. Why you are sad? You did a lot of hard work to find out the model and the model is behaving poorly. If the statistics fall in this region, you're happy. You say reject H null, right? You say reject H null. I'm happy. Okay. Now there is a very important discussion that is being done. Now this one is a new inclusion in the syllabus, in some of the syllabus, not in every curriculum. So they are trying to compare the T test and F test. For what? For not for model, for coefficients. So they are saying that you should not use T test, you should use F test. What is the logic? Let's understand. So you're saying y is equal to b0, b1, x1, b2, x2 plus b3, x3 is your model. When you're testing b2, you're only testing b2. You're not thinking about b1 and b3. When you're testing b3, you're not thinking about b1 and b2, right? You do not respect the correlation, whatever the minimum correlation. You don't want the correlation between x1 and x2, but there is a correlation between them. There is some impact of x1 on x2 or x2 on x3, right? You are saying that there is no impact. And because of that assumption, your test is not performing pretty good. So how to apply the coefficient test on the overall model? So they are saying, assume this is your model R. This has only one variable, that is y is equal to b0 plus b1 x1 plus error term A, or you can say error term of R, because I'm calling it as R, model R. There is another model U. Why I'm calling it as R and U, I will talk about it in a minute. The another model is extension of the model where you're adding the variable x2, x3, and I'm calling the error as error U. So this is model R, this is model U. Why I'm calling it as model R? Because it is a restricted model. It has only one variable. Why I'm calling this as model U? Because it is an unrestricted model. It has a lot many variables into it. Okay. Now if you compare model R and model U, it is actually you should understand that when you adding the variable, then the error of the model should decrease. We discussed about it. More number of variable, the error will decrease. So the error of the model will decrease where in model R or U. Tell in model R will error will be less, or in model U the error will be less. Model U, because you have number of variables higher the number of variables. Now sum of squared error of R, what is that? That is the volatility of standard deviation of model R, the volatility of error, the volatility of error term, the volatility of the error term of model R. And what is SSU? The volatility of the error term of model U. Okay, so model R has a SSE, model U has a SSE. Where the SSE would be lower? Again, U or R? So you are saying, okay, the error is falling. Error is falling. Let's calculate the percentage of fall. So for any percentage change, like a price change, what you do? P2 minus P1 upon P1. So I should have done, okay, it is falling. So SSE of U minus SSE of R upon SSE of R, previous minus initial upon initial, right? Now the problem with this equation is that it will give me negative value. So I tweak it and I am saying that why not do it otherwise? Why not do it otherwise? Because SSE U will be always lesser than SSE R. So I'm saying SSE R minus SSE U upon SSE EU. So what I am doing? I am doing initial minus previous upon previous. Initial upon initial minus previous upon previous. I just slightly tweak the formula to make it positive, because F stats or F distribution is always respecting the positive values. So this is my F stats. Okay. Now in F stats, definitely you need the degree of freedom. So there is a degree of freedom. Now the degree of freedom of SSC is always what? N minus K minus 1, because that is a full model. So SSC U is in the denominator. So you have to divide with the degree of freedom of the U model. The U model has 3 variables. N is the number of observations, so N minus K minus 1. And SSCR minus SSCU, the degree of freedom, is the number of extra variables that you have. So the number of extra variable is 2. That is your F stats. And then again you do the same stuff. But here, what you're saying when you are adding B2 and B3, I'm only testing B2 and B3. I'm not testing B1. Because this is a comparison between a model R where we have only one variable x1. In model U, we have two variable x2 and x3. So I just have to test B2 is equal to B3 is equal to 0, and I have to test B2 not equal to B3 equal to 0. At least one of them should not be equal to 0. So this is the test of B2 is not equal to 0, B3 not equal to 0. Again, you want your F stats to be higher, because you want the B2, B3 when you're including B2, B3 as an X2, X3, your F stats, this difference should be very higher. Initial minus previous or previous minus initial should have a very high value, and therefore you want it to be higher, because it is adding the extra unexplained into explained section, the x2 and x3. You want it to be higher, and therefore you say if F stat is falling in this region, you are rejecting the null hypothesis, and you will say no, B2 is not equal to 0 and B3 is also not equal to 0. So again you are testing the B2 and B3 individually, but in comparison to the previous model, and this is the right way to do, because you're respecting the correlation between x1, x2 and x3. And therefore they say that why to do the coefficient testing with the t test, do it with the F test. समझ में आया? Now the last section is the assumption of the model. So there are multiple assumptions that we already discussed. We said that there should be linearity in the parameter. We said that the error term should be independently normally distributed with a mean of 0 and a constant variance. We said there should not be any linear relationship between the independent variable x1 and x2. There should not be any correlation between x1 and x2, x2 and x3, right? Right now we are only talking about what if these assumption does not hold true. That means there is a violation of regression assumption. And if there is a violation, what kind of a violation it would be? What would be the effect on the model, and how you detect it and how you correct it? So the first violation is of constant variance. We are assuming the variance is constant. If that is a violation, what it is, what is the effect on the model, what and how we can detect it and how we can correct it. if there is a correlation between x1 and x2, or x1, x2, x3 are linearly related, that will lead to the problem of multicollinearity, how it will affect the model, how you can detect it, and how you can correct it. And if error term is not independent, error term is dependent upon the previous error term, then what will happen? Okay, if it is the correlation between the error term, this error term with the previous error term is not equal to 0, that will create a problem of autocorrelation or serial correlation. What is the effect? How you detect it and how you correct it. So let's start with the assumption of the model. So if there is no constant variance, it will lead to the problem of heteroscedasticity. So you need to understand what is it, affect, detect, and correct it. Similarly, if there is a correlation between the independent variable x1, x2, x3, x1, that is a problem of multicollinearity, and the error term is dependent upon its previous value. Error term is dependent upon the previous value. Error term could say dependent, and that is the problem of serial correlation or autocorrelation. Okay, so you have to understand what is it, effect on the model, detect it, and correct it. Okay, first of all, let's understand heteroscedasticity. What is it? When error term is not constant. Okay, error term has to be constant with a normal distribution with a mean of 0. This is image 1. Can you see the error? Yes, you can see the error. There is image 2. There is error. In which of the image 1 or image 2, you feel that the error term is constant? Image 1. So therefore I have written homoscedastic. Homo means constant, skedastic means variance. Hetero means non-constant, skedastic means variance. So you can see image 2 is what? Heteroscedastic. As in error term, sometimes the variance in the error term is high, sometimes it is low, sometimes high, sometimes low, sometimes high, low, high, right? And it is not constant. Here the variability of error term is constant. The variability of the error term is constant. I want this. That is the assumption of my model. However, there are two kinds of heteroscedasticity. One is called conditional heteroscedasticity. Another is called as unconditional heteroscedasticity. Let's understand with the help of image. Image 1, image 2, image 3. Where you felt there is a problem of unconditional heteroscedasticity because you can relate to the word unconditional pretty easily. There is in unconditional image 1, 2, or 3.